Let's think about an example permutation, which I've written at the top here, called T. So if we're going to draw a picture of what T does, we might do it by drawing an arrow from the input to T to its output. So T of 1 is equal to 2, so I might draw an arrow from 1 to 2, like this. And T of 2 is equal to 3, so I'll draw an arrow from 2 to 3. T of 3 is equal to 1, so I draw an arrow from 3 to 1. And you can see that what T does is to send these numbers 1, 2 and 3 round in a cycle. So for that reason, permutations like T are called cycles, and they turn out to be very important to us. So what we're going to do in this lecture, to begin with at least, is to generalize this idea of a cycle and to come up with some notation for cycles. So here is the definition. You pick a whole number m, positive whole number m, and you pick some distinct positive integers, a0 up to am minus 1. Then the permutation which we write like this, so brackets a0, comma a1, comma up to am minus 1, close brackets, that's defined to be the permutation such that the number ai goes to ai plus 1 for I less than m minus 1, and the number am minus 1 goes back to a0. Furthermore, if you've got any number which isn't one of the ai's, then this permutation sends that number to itself. So let's draw a diagram of what's going on. In the spirit of the diagram I already drew, what's happening is that a0 is sent to a1, a1 is sent to a2, a2 is sent to a3, and so on until we get to am minus 1, which is sent back to a0. So when you reach the end of the cycle here, then you go back to the start. To understand this, it helps to look at an example. So let's look at an example which is the permutation whose cycle notation would be 5, 2, 4, and which I think of as a permutation in S5, so a permutation of the set 1, 2, 3, 4, 5. If we want to record what this permutation does in a different way, we might write down its two-row notation. So on the top row I have to have 1, 2, 3, 4, 5, since I'm thinking of this as a permutation in S5. And we then have to think, what does the definition say? Well, the definition says that A0 goes to A1, A1 goes to A2, and so on until you reach the end of the cycle when you go back to the start. So for us, 5 would go to 2, so I should write a 2 beneath 5. 2 would go to 4, so I should write a 4 beneath 2, and 4 would go back to 5 again, so beneath 4 I should write a 5. And then the other rule in our definition is that any number which is not in the cycle is simply sent to itself. So the numbers not in our cycle are 1 and 3, and 1 should go to 1 and 3 should go to 3. So that would be the two-row notation for this cycle here. Let's make one more observation before I move on, which is I had to tell you that this cycle 524 was an element of S5, because if you just look at this cycle on its own, you can't tell whether this is supposed to be a cycle in S5 like this, or a cycle in S6 whose two-row notation would be exactly the same, except it would also have 6 going to 6, or it could be an S7 or an S8 or an S9 and so on. So when we write cycles like this, we need to remember that it's not obvious which symmetric group these cycles belong to, and if you want to make that precise, you have to actually say so. So this might look like a drawback, but actually it's useful. It's a useful property for cycle notation as long as you remember it. Okay, let's now make precise our definition about what is a cycle. So this definition here is that a permutation of the form which we've just written down is called an M cycle because there were M things inside the cycle here. and a permutation which is an m cycle for some m is just called a cycle. Right, there is a special case of the definition of cycle, which is a one cycle. And the reason we have to be a little bit careful for one cycles is that every one cycle is just the identity permutation. If you think about the definition of cycle, well, the definition was everything outside the cycle is sent to itself, and everything inside the cycle goes around in a circle. So if you have a cycle with just one thing, I, in it, well, then it will go round the cycle and back to I again. So a one cycle would send everything to itself, so it would be the identity permutation. And that's one of the reasons that we avoid writing one cycles. The other reason is even worse, that if you write I, it looks a little bit like you're applying a function to the input I, and that is confusing because we want this I to be a one cycle. So for both of those reasons, we tend to avoid writing down one cycles when we can. Next thing I want to say about cycles is that we can write the same cycle in cycle notation in several different ways. So to see what I mean here, let's consider the three cycle 1, 2, 3. So in two-row notation, what does this do? It sends 1 to 2, 2 to 3, and 3 back to 1 again. Let's now think about the three cycle 2, 3, 1 and try and work out its two-row notation. Well, it sends 2 to 3, it sends 3 to 1, and it sends 1 all the way back to 2. Again, consider the three cycle 3, 1, 2. What it does is send 3 to 1, 1 to 2, and 2, 1 to 2, and 2 back to 3. Okay, well, look at all of these things. We got the same thing each time, right? Each one of these two-row notations was the same. So the three cycle 1, 2, 3 and the three cycle 2, 3, 1 and the three cycle 3, 1, 2 are all the same permutation. And in general, an M cycle can be written in cycle notation in M different ways, because you can choose any particular number to start the cycle with. So as another example, if you had, for example, 1, 3, 2, 4, you could also start that cycle with the number 3, in which case it will be equal to 3, 2, 4, 1. And you could also choose to start it at 2, in which case it will be equal to 2, 4, 1, 3, or 4, 1, 3, 2. So you have to be careful with cycle notation. The same M cycle can be written in M different ways because you can choose any of M different numbers to start your cycle with. Last definition for this lecture is disjoint cycles. So this is a really simple definition. Two cycles are called disjoint if none of the numbers in the first cycle are equal to any of the numbers in the second cycle. So for example, if we take 1, 5, 2 and 3, 4, 7, those are disjoint cycles. But if we take 2, 4 and 5, 2, 1, 3, those things are not disjoint because they have a number in common, namely there's a 2 in both of the two cycles. So there's a good reason to be interested in disjoint cycles, which is something that you are going to prove on one of your problem sheets. And that reason is that we know in general, if you take two permutations, So let's say f and g in Sn. It's not always true that f composed with g is equal to g composed with f. So in general, f composed with g is not equal to g composed with f. But if f and g are disjoint cycles, then they do commute with each other. So to summarize that, we say disjoint cycles commute.